The energy bands are aligned at the same vacuum level. So see here, the final vacuum level, you see the vacuum level for both metal and the semiconductor is going to be same. That is one thing. The uppermost energy level, which is the vacuum energy level, is going to be same for metal and semiconductor junction when a contact is going to be made. When the metal and semiconductor layer regions are brought together, the Fermi levels do align themselves at thermal equilibrium. The condition that exists just before the thermal equilibrium is depicted. Yes, so before equilibrium you have this condition, and after equilibrium you have this condition. This is the Fermi level of metal, and this is the Fermi level of the N-type semiconductor. So after you join these two and make a contact, you can see that the Fermi levels are getting aligned. So you can see the Fermi level of metal is comparatively the lower energy band than the Fermi level of your semiconductor junction. So the phi b is the potential barrier height of your Fermi level of metal, and band edge where the minority carriers exist. See the diagram phi b. So phi b is the energy level from the conduction band of semiconductor to the Fermi level of your metal. Okay, so the metal side, the Fermi level is the lowest energy level, and from the lowest energy level till the highest energy level of the semiconductor EC, that I am going to denote it by phi b. Phi b is the barrier height, or I can say it is the potential difference between the Fermi level of metal and the conduction band where the majority carriers are existing. So for N-type semiconductor, the barrier height difference is given by the metal function. So the barrier height for N-type, they are giving it by phi Bn. So phi Bn equal to phi n minus x. So phi b, this I want this total barrier height is phi m, and this barrier height is x, or I can say it is x. So if I want to find this phi b alone, so it should be phi m minus x. That is what from the diagram you see, this total thing is phi m, this thing is x. So if I want to find phi b equal to phi m minus x. That is what is given here. This equation is given as per the energy band diagram, and this x is called as electron affinity. So all these are hardcore physics parameters. So you can go and study it in depth if you require. Otherwise, just understand that for N-type semiconductor, the barrier height is going to be the difference between the total work function of your metallic region and the electron affinity x. The same thing if you go for a P-type, you will get this one. X, the ulta, you will get the ulta x minus phi m plus Eg by Q. So Eg is going to be the energy band gap between the conduction band and valence band. So you know that for P-type material, the Fermi level is going to be near the valence band. So the complete construction of P-type metal semiconductor junction is going to be different. So you need to have from the conduction band till the end of the valence band, and near the valence band you will be having the Fermi level. So you will definitely have what is called as Eg. But in N-type, Eg will not come because my Fermi level is above the valence band of my N-type semiconductor. So when you go for P-type semiconductor, the Fermi level will be even more here. So it will be close to valence band. So you have to consider the entire conduction band energy difference from the conduction band to the valence band. But here I am considering from EFM only because EFM is slightly higher than the valence band of your semiconductor junction. And if you add both phi Bn plus phi Bp, if you add both, you can see this phi m will get cancelled, phi m will get cancelled, x will get cancelled, so you will get Eg by Q. Or I can write energy band gap Eg is equal to Q into phi Bn plus phi Bp. Okay, so if you add the barrier height for N-type and P-type, and if you multiply that with the charge, that will be equivalent to the energy band gap of the semiconductor junction. So this is the relation between the barrier height and the energy. Barrier height into charge will be equal to the energy level and our forbidden energy gap between the N-type and P-type substrate. So in metal, we are going to focus only on N-type, okay? So we will not be focusing on P-type, where specifically where you have a P-type semiconductor, we'll be using the equations for P-type. Otherwise, we'll be going with only N-type semiconductor junction. So in the metal semiconductor junction, a barrier is formed if the Fermi level of metal is somewhere between the valence band and conduction band edges of the semiconductor. Yes, that is happening. See the diagram. The Fermi level of metal is between EC and EV. So you have a barrier being formed. Okay, and you also that barrier will have a built-in potential phi on between, which is going to be defined as the difference between the Fermi level of metal and the Fermi level of the semiconductor. So the total built-in potential will be the difference in Fermi levels of metal and uh, semiconductor regions. For n type, the same formula. See here, phi bn equal to phi m minus x. So take this phi m minus x, and this x is electron affinity. Electron affinity is given by the difference between the energy band in conduction band and Fermi level, EF minus EC minus EF by Q. Okay, so the phi 1n means it is the built-in potential of the n-type semiconductor region. So phi 1n equal to phi bn minus this value, and phi bn substitute this one, phi m minus x minus EC minus EF by Q. If you take for p type, so it will be the reverse. So phi 1p equal to this minus x will become plus x, plus phi m will become minus phi m. Here you have to subtract the Fermi level minus the valence band, because you see in n type a conduction band and then Fermi level comes. So I write EC minus EF. If you write for p type, first your Fermi level will come, then your valence band will come. So it is EF minus EV. So the difference you can understand. So nothing to by heart here. The energy difference, we are considering only the Fermi level. So in n type, we are going to have the majority carriers are going to be electrons. So the Fermi level is close to conduction band. That is going to be defining the built-in potential. In p type, the majority carriers are going to be holes, and the Fermi level is going to be close to the valence band. So that difference is going to give me the impact of the potential barrier. So we have derived the potential barrier or built-in potential between the for the n-type and p-type semiconductor in a metal semiconductor junction in a MESFET device. And you know that the Fermi level formula as per unit 1, you should be recollecting all these formulas. The Fermi level formula for n-type semiconductor and the Fermi level energy band formula for p-type semiconductor. So EC equal to EC, EF equal to EC minus, because the Fermi level is below the conduction band, minus KT ln NC by ND. NC is the number of electrons in the conduction band, ND is the number of donor atoms. And for p-type, EF equal to EV plus. Why EV plus? Because the valence band is lying above the conduction, Fermi level is lying above the valence band. KT ln NV by NA. NV is going to be the number of carriers in valence band, and NA is going to be the number of acceptor atoms what we are going to dope. So in the same way, I can see from the two equations, I can find what is EC minus EF and what is EF minus EV. So if I find these two and if I substitute in the previous two expression for the built-in potential, I can write phi 1n equal to phi bn minus EC minus EF by Q minus x. That is the expression what we have. And EC minus EF is going to be KT ln NC by ND. So I'm getting phi bn minus KT by Q ln NC by ND for an n-type semiconductor. And if you find EF minus EV, it is going to be KT ln NV by NA. So it is phi 1P is going to be phi BP minus EF minus EV by Q. That is going to be phi BP minus KT by Q ln NV by NA. This is going to be for a p-type semiconductor. So I am ignoring this X. Or I am writing, or I am using only this first formula, phi bn minus EC minus EF by Q. I am not using this phi m. I am using this direct formula for phi bn, and here I'll be using the direct formula for the thing phi bp minus EF minus EV by Q. So I am not bringing here phi m and x. So this is the built-in potential of the metal semiconductor junction involving P-type and N-type semiconductor. So N-type means accordingly you have to consider the concentration of electrons in the conduction band and number of donor atoms. And P-type means we are going to consider the concentration of majority carriers in the valence band and the acceptor impurity concentration. And you know KT by Q is going to be the thermal voltage Vt. Okay, KT by Q is Vt. So I can replace this KT by Q by thermal voltage Vt if required. So phi 1n will be equal to phi bn minus Vt ln Nc by Nd. Phi 1p equal to phi bp minus Vt ln Nv by Na. So these two are the equations what we get for the built-in barrier potential for N-type and P-type semiconductor in a metal semiconductor junction.